Exploring Life. Chapter 10, Energy. Part 2. Energy is critical for maintaining life. Without a steady supply, everything would come to a halt. Living systems rely on a constant input of energy to keep functioning. So, where does that ongoing energy input come from? The two primary sources are solar energy from the sun and geothermal energy from deep within the earth, primarily generated by radioactive decay. Additional sources, such as cosmic radiation or gravitational energy from the moon and sun, make only a negligible contribution, as no known organisms harness them directly. However, gravitational forces do influence tides and contribute slightly to internal heating through friction. Together, these energy sources power everything, from global weather systems to the tiniest cellular processes. Just like a paycheck covers your expenses, this steady energy income keeps life running, even as entropy quietly takes its cut. Some organisms can, and do, harness geothermal energy, tapping into the heat that comes from deep within the earth. For example, certain bacteria, algae, and archaea thrive in hot springs, using both the intense heat and surrounding chemicals to survive. Even more extreme, some organisms live in complete darkness near deep-sea hydrothermal vents, where they rely entirely on geothermal heat and chemical reactions, not sunlight, for energy. This is a hydrothermal vent ecosystem on the ocean floor. The scale bar shows 1 meter, reminding us just how massive and active these deep-sea systems can be. Superheated water, rich in minerals, escapes through cracks in Earth's crust, creating an extreme but energy-rich environment. Organisms like tube worms, shrimp, and heat-loving microbes don't rely on sunlight. Instead, they survive on geothermal energy and chemical reactions, a process called chemosynthesis. And what's more remarkable? They thrive in complete darkness as the sunlight does not reach the depth of the ocean. Hydrothermal vent ecosystems are rare but ecologically vital, supporting unique life forms and offering insight into how life might exist beyond our planet. The Sun, the central star of our solar system, is enormous, about 1.4 million kilometers in diameter. That's large enough to fit over 1 million Earths inside. As we mentioned in our chemistry lectures, the Sun is powered by nuclear fusion and functions as a colossal thermonuclear reactor. It constantly emits energy across the electromagnetic spectrum, including forms that can be harmful to life. Occasionally, this energy surges in the form of solar flares, which you can see in this video. These are sudden bursts of magnetic energy from the Sun's atmosphere. Even medium-sized flares can form arcs several times wider than Earth. From 93 million miles away, the Sun delivers about 1.74 multiplied by 10 to the power of 17 joules of heat energy to Earth every second. That's an enormous amount of thermal energy, over 5,000 times greater than the heat produced by Earth's interior. Of this energy, about 30% is reflected by clouds, atmospheric particles, and surfaces, while 70% is absorbed by the atmosphere, oceans, and land, warming the planet. Without the natural greenhouse effect, Earth's average temperature would be -18 degrees Celsius, or 0 degrees Fahrenheit, cold enough to trigger a new snowball Earth period and complete global glaciation, similar to what we discussed in the previous lecture. Greenhouse gases, such as carbon dioxide, methane, and water vapor, trap a portion of the infrared radiation re-emitted by Earth's surface, slowing the loss of heat to space. This process maintains a stable average temperature of 15 degrees Celsius, or 59 degrees Fahrenheit, making liquid water and life possible. This immense source of free energy, the sun, has shaped life on Earth, driving the evolution of adaptations that both harness its power and protect against its potential harm. Heat energy, in the form of infrared radiation, warms the planet, drives climate and weather systems, and helps maintain the conditions necessary for liquid water and life. In addition to heat, the sun provides light energy to the planet, and living organisms evolved the ability to capture and use it. Light energy powers photosynthesis, enabling plants, algae, and some bacteria to produce food and release oxygen, laying the foundation for nearly all life on Earth. Through food chains, the energy captured by photosynthesis spreads through ecosystems, supporting nearly all living organisms. All life on Earth can be grouped into two main categories based on how organisms obtain food, the form of energy that living organisms use. Autotrophs, producers, organisms that can make their own food, typically through photosynthesis, using sunlight, or chemosynthesis, using chemical energy from inorganic substances. Heterotrophs, consumers and decomposers, organisms that cannot produce their own food. Instead, they rely on consuming other organisms or breaking down organic matter to obtain energy. Together, autotrophs and heterotrophs form the foundation of energy flow in ecosystems, from capturing energy to recycling it through food webs and nutrient cycles. The schematic image illustrates the relationship between producers, consumers, and decomposers. The sun's energy is shown here as the starting point. Cyanobacteria and plants use photosynthesis to harness sunlight, acting as primary producers that support all other life. Their stored energy is then passed on to consumers, organisms that eat plants or other animals. Finally, decomposers break down both plant and animal matter, recycling nutrients back into the ecosystem. This continuous flow, from sunlight to producers, to consumers, to decomposers, forms the foundation of life on Earth. Let's take a closer look at each group, starting with the producers. Producers, or autotrophs, are organisms that can create their own food. Some, known as chemoautotrophs, use chemical energy instead of sunlight in a process called chemosynthesis. They still produce sugars and are both interesting and important, but we won't spend much time on them in this course. Our focus will be on photoautotrophs, the most common and ecologically significant producers. These include plants, algae, and cyanobacteria, which use solar energy to power photosynthesis. Through this process, they convert sunlight, water, and carbon dioxide into sugars, releasing oxygen as a byproduct. Autotrophs form the foundation of the food chain, providing the energy that sustains nearly all life on Earth. Heterotrophs, which include consumers and decomposers, cannot produce their own food. Instead, they rely on organic molecules made by autotrophs to meet their energy needs. They extract this energy through cellular respiration, a process that breaks down sugars to fuel their cells and support life functions. Heterotrophs play a vital role in both transferring energy through food chains and recycling nutrients within ecosystems. This group includes animals, fungi, and many types of bacteria. Whether it's produced by the organism or obtained by consuming others, the energy stored in food must be converted into a usable form. That's where cellular respiration comes in. Both autotrophs and heterotrophs rely on this process to extract energy. Autotrophs produce sugars through photosynthesis, but they still need to break those sugars down through cellular respiration to power their own cells. Heterotrophs consume organic matter and use cellular respiration to release the stored energy in that food, fueling growth, movement, and other essential life processes. Once the energy in food is released, the story doesn't end there. Within living organisms, chemical reactions are constantly occurring, some that consume energy, and others that store it for later use. Importantly, energy is never created, it is only transformed, and it always moves toward dissipation, in accordance with the second law of thermodynamics. And even as it gradually dissipates, energy still powers everything, from growth and repair to cell maintenance and the transfer of energy between molecules. This continuous flow and transformation of energy is essential for life. Without these energy-driven reactions, life as we know it wouldn't be possible. Let's recall that endergonic reactions require an input of energy to proceed. In these reactions, the products store more energy than the reactants, making them essential for building complex molecules. One important example, which we'll explore in more detail, is photosynthesis. In this process, plants absorb sunlight and store that energy in the chemical bonds of glucose molecules. Endergonic reactions are vital for growth, repair, and long-term energy storage in living organisms. Let's recall that endergonic reactions require an input of energy to proceed. In these reactions, the products store more energy than the reactants, making them essential for building complex molecules. One important example, which we'll explore in more detail in the next chapter, is photosynthesis. In this process, plants absorb sunlight and store that energy in the chemical bonds of glucose molecules. Endergonic reactions are vital for growth, repair, and long-term energy storage in living organisms. Exergonic reactions release energy that was previously stored in molecules. Fortunately, molecules don't spontaneously fall apart. These reactions usually require a small input of activation energy to begin. In living organisms, a key example is cellular respiration, which we'll be studying as well. During this process, glucose is broken down, and the released energy fuels essential cellular functions. Exergonic reactions are vital for life. They break down complex molecules and provide the energy needed to power everything from movement to metabolism. This image illustrates the chemical relationship between photosynthesis and cellular respiration, two reactions that mirror each other. Photosynthesis is an energy-storing process. Plants absorb sunlight to convert carbon dioxide and water into glucose and oxygen. Cellular respiration is an energy-releasing process. Cells break down glucose in the presence of oxygen, producing carbon dioxide, water, and usable energy, ATP. Together, these two reactions form a biological energy cycle, with photosynthesis capturing and storing energy, and respiration releasing it to power life. Living organisms carry out thousands of chemical reactions, both endergonic and exergonic, far beyond just photosynthesis and cellular respiration. The term metabolism refers to the sum of all chemical reactions that occur within an organism to sustain life. Metabolism includes two major types of pathways. Catabolic pathways, which break down molecules and release energy. Anabolic pathways, which build complex molecules and consume energy. These continuous energy transformations are essential for life, fueling everything from growth and development to repair and maintenance. In several previous lectures, we discussed the major energy molecule used by living organisms, ATP, or adenosine triphosphate. ATP serves as the cell's primary immediate energy source. It works by transferring its third phosphate group to other molecules, a process called phosphorylation, which energizes those molecules to perform work. ATP is a dynamic, short-term energy carrier, constantly being used and regenerated to power everything from muscle contractions to chemical reactions inside cells. But it's important to remember, ATP isn't the only energy-storing molecule in living systems, just the most immediate and versatile. Living organisms use several types of energy storage molecules, each suited to different timescales and biological functions, as illustrated in the table. ATP serves as a short-term energy currency, providing immediate energy for cellular processes. For medium-term storage, plants store sugars as starch, while animals store glycogen in the liver and muscles. These molecules can be broken down quickly when the body needs a rapid energy boost. For long-term storage, plants store energy as oils, and animals store it as fat. These reserves can be metabolized when energy demands exceed immediate supply. For medium-term energy storage, organisms rely on more stable forms of energy storage. Plants convert excess glucose into starch, which they store in roots, tubers, and fruits. Animals convert glucose into glycogen, a polysaccharide stored primarily in the liver and muscles. These molecules, starch and glycogen, have already been introduced in previous lectures and serve as reliable, accessible energy reserves. For long-term energy needs, organisms store energy in the form of lipids. Plants store excess energy as oils, especially in seeds and nuts. Animals store energy as fat, which is deposited in specialized tissues throughout the body. Lipids provide the highest energy yield per unit of weight, making them an efficient and compact form of energy storage, ideal for surviving periods of scarcity or dormancy. Let's make sense of energy storage with a financial analogy. ATP is like having coins in your pocket, perfect for small, immediate purchases, but not practical to carry in large amounts. Polysaccharides like starch and glycogen are like paper bills, great for medium-term use, easy to carry, and ideal for quick energy access. Fats, lipids, are like a debit card linked to your savings account. You can tap into a large reserve when needed, and it's far lighter than lugging around coins or stacks of cash. Just like living organisms, the planet can store energy too. Normally, when an organism dies, the energy in its organic matter fades away quickly. But under the right conditions, deep burial, low oxygen, and a lot of time, that energy can be preserved for millions of years. This is how Earth builds its long-term energy reserves, fossil fuels, created from ancient life. Coal comes from the remains of ancient plants. Oil and natural gas come from tiny aquatic organisms. Over millions of years, heat, pressure, and a process called diagenesis transformed this buried organic matter into the fossil fuels we rely on today. But when we burn fossil fuels, we release that stored energy back into the system. Follow the prompt and see how much you recall from the topics we've covered. Don't worry if you don't remember everything, review the materials as needed, and use this as a chance to learn even more in the process.